Hello, I want to solve our same ODE by the technique of exact ODEs. Okay, so here we have our dy dx is minus 3 times y minus 20. Well, for exact ODEs, we kind of like x to be the independent variable. Okay, so the first thing we have to do, we want to convert to okay, we want to convert it to this differential form, so-called. And then if you check the partial derivative of this coefficient with respect to the other variable, the y variable, and this coefficient from the dy with respect to the other variable. And if so, the ODE is exact. And the solution is psi of x and y equals a constant. That's going to be the kind of the general solution, the solution with an arbitrary constant in it. Okay, and we'll get to that in a bit. Let's just do it for this one. All right, so the thing about this is not in this differential form yet. Okay. All right, let's try to put it in there. So we can get dy is minus 3 times y minus 20 dx, right? Or bringing that over, I get 3 times y minus 20 dx plus dy equals 0. So this is in differential form. Right? So the question is d dy of this thing, 3y minus 20, is that equal to the partial derivative with respect to x of, I don't see anything there, but there really is something there. There's a 1 there, right? I don't see a coefficient. That means the coefficient in front of dy is 1. And then what is it? Is 3 equal to 0? No. Therefore, okay, well, it's not exact in this differential form. Differential, okay? So this is not exact. Okay, well, we might think we want to go on, but they say we're told to solve this, okay? So, in fact, we had this thing called mu way back in this review. We found that mu of x is e to the 3x. Okay, is the integrating factor. Okay, and so in fact, if I take this whole thing and multiply this whole form by e to the 3x, so we can do this. Another differential form of the ODE is, I just take this, multiply everything by e to the 3x. I get 3 e to the 3x times y minus 20 dx plus e to the 3x dy equals 0, right? All right. So how, right? So now I want to check if this is exact. Okay, this wasn't exact, but this is actually the same. This is actually the same differential equation, right? Because I just multiply by some non-zero function. So is this exact? Well, I can take the dy of this thing. Does that equal the dx of e to the 3x? Well, I differentiate this with respect to y, treating x as a constant. I just get 3 e to the x. Does that equal to the derivative of this? I get 3 e to the 3x times 3 from the chain rule. Yes, they are equal. This new ODE in differential form is exact. Okay, now that's another way of thinking of what this magic factor, this mu, this integrating factor is. It's the thing, if I guess it's the thing that I have to multiply the previous form without the e to the 3x by to make this exact. Okay, and how did I come up with it? Well, don't worry about it. If you had taken this class 100 years ago, you would have probably spent a lot of time learning how to figure out what these integrating factors are, what these mu, they can be mu of x and y, what they have to be for various situations. But we don't worry about that too much now. So I might tell you to use an integrating factor, like say use this integrating factor of e to the 3x, but you don't have to come up with it yourself. All right, so that means, so what this means is the solution to the ODE, no initial conditions yet, the ODE is psi of x and y equals constant, where d psi dx is 3 e to the 3x times y minus 20, and d psi dy is e to the 3x, okay? In other words, when I show that this ODE is exact, what I really am saying is that this is another form of d psi dx plus d psi dy equals 0. This is sometimes called d psi is 0. This is the differential d psi for a function of two variables. Psi is a function of x and y. There's d psi. So d psi is 0. Psi is constant on curves. Psi is constant on curves. All right. So let's go ahead and do that. And we like to I like to give these names. This is Roman numeral 1, and this is Roman numeral 2. So 1, okay. What 1 gives that this function psi of x and y, I know what its derivative is with respect to x. So I can just do the integral. Now I have a constant of integration, and that constant of integration is going to be a function of y. It's a constant as far as x is concerned. That means it could be a function of y. All right, so let's do that. That's all a constant. 3 is a constant, but in the integral of e to the 3x dx is e to the 3x over 3. So this is pretty easy. The 3 goes away. I get e to the 3x times y minus 20 plus h of y. So So psi of x and y is e to the 3x times y minus 20 plus some arbitrary function of y, okay, is kind of, I think of this as like the partial answer, okay? Halfway through. Okay, so now use 2, and sometimes it's going to be maybe take care of 1. Sometimes it's going to be have a little bit more bite than this one. But now I'm going to just take this partial answer and plug it into here. So what happens if I take d psi dy for this? Well, d psi dy for this is, well, the only thing that multiplies y is e to the 3x, and then plus h prime of y. That's the derivative of this expression with respect to y. Oh, and I'm told that that's got to be e to the 3x. That's what 2 says. Okay? By the way, this is a really good check. When I've done this, see that all the x's go away. Therefore, I find that h prime of y equals 0. And if you do this and you find that h prime of y is 3x, you're screwed, right? H prime of y has to be a function of y only with no x's. Sometimes you find h prime of y is y squared, so then h of y is y cubed over 3 plus a constant, right? All that. All right? So this method has a self-consistency check when you do this. Well, this is easy. So h of y is equal to, I'm going to call it c twiddle. All right? So that means I know exactly, that means that this this constant here, this thing says that, so the solution is e to the 3x times y minus 20 plus what I called c twiddle. Sometimes I get a real honest to goodness non-constant function of y when I do this, and that equals c. Okay, well, heck, I can just bring this over. A new c is c minus c twiddle, or e to the 3x times y minus 20 is c. Okay, that's good. That's an implicit solution. It's usually all that you get when you do this. But heck, we can actually find an explicit solution, which is to be preferred. I can actually solve this for y, right? So I can solve this. An implicit solution there for y. And I get y minus 20 is c over e to the 3x, dividing both sides by 3x. And I kind of prefer to call that e to the minus 3x on top instead of e to the plus 3x on the bottom. Or y is bringing the 20 over, 20 plus a constant times e to the minus 3x. So yet another way of obtaining the solution to this differential equation. Probably one of the hardest we've done so far, but okay. All right, bye.